or record it. That should be that in regards to lecture. We'll just leave it at that. So for the lab for this upcoming week, I'm going to give you several variables and you get to choose which ones you want to look at. The idea is to have a bivariate analysis. So we just finished talking about that last week. It's when you're looking at two different variables and seeing their relationship in one way or another. When we talked about it last week, remember we had kind of that weird example of what's the relationship between the number of firefighters present and the amount of damage on property. And there's kind of this overarching variable, right? Do you guys remember what the overarching variable was? I know it was a long time ago, last week. The size of the fire was the overarching, right? So it's not so much that there's a lot of damage done to your house because there's a lot of firefighters traipsing through your property. There's a lot of firefighters because the fire is larger. And because the fire is larger, that is causing more damage to your property, right? Does that kind of ring a bell from lecture? Okay. So one of the examples that we talked about, that specific one, there was also a table, and that was a crosstab table. Now you guys have done this. The very first lab was also doing it. Sorry, let me add people here. The first lab, you guys had to do a crosstab between gender and level of education to see if there was a significant difference or if there seemed to be a pattern between the different levels of education between not finishing high school, bachelor's, and then upper level, and then gender. And then you had to do it again with race to see if there was any patterns that were seen in that specific data set. This time it's going to be a little bit different. I'm going to give you a data set and you get to ask a question of it. And this is a preview of what the final project is going to be like. The final project, again, for this class is part of the final in a way. It's something that I'll introduce. I'll probably introduce it on the 21st. This way you have a little extra time to work on it. You do not need to gather data. You don't need to do any outside research. It's straight statistic. I will give you a data set and you guys will have to run some analysis based on some parameters that I give you. So I may tell you something like run 3 separate analysis on descriptive statistics. So I need you to include a mean, a standard deviation, something like that. Okay. So the lab that'll be due next week is a tiny taste of that. Okay. You will be asked, and I'll add some additional information because I think here, whoops, let's see what it says. I just want to make sure that is, it's got the correct instructions. Yeah, so here it is. Turn in your analysis. Okay, let me see. Just add a little bit more. So you'll need to include 1 mean, 1 median, 1 standard deviation, and 1 crosstab. So it's technically 4 separate analyses so that you guys have that all correct. And I want to include this last piece right here. Whoops. That's not right. Sorry, guys, I'm just trying to pull this up here. Here it is. Okay, I want to share my screen so that you guys can see exactly what it'll look like. Here it is. I don't think you can see my screen, can you? No.
No, I only see you.
You only see me. Can you see it now?
Yeah, it's starting to share.
Okay, I don't know what was going on there. Okay. This is the analysis that you're going to look at. At the very top, you're going to see the question or the variable name. This is select gender. You'll notice 3 different types. There's female, male, prefer not to say, and I think those are the only options. Yes. here's a few questions to consider. So do you eat more or less food now that you are in college? Have you gained or lost weight since starting college? When do you snack? And notice this one is a multiple response. So this may be a tricky one if you pick this one, because the participants could respond or select multiple answers. So you see the first one says when bored and between meals, while this person here said when bored, between meals, and while doing homework. So there's multiple responses, and others just said when bored or if needed. This variable is, would you say you eat more or less since the start of the pandemic? And this last variable, actually, it looks like I need to add age as the title. I got a little wonky. Age. There we go. And it looks like we have 3 people who didn't answer their age. Okay, so based on this, you're going to need to create an analysis of mean, median, standard deviation, and one question that you ask of the data that would be a crosstab, which is like inserting a pivot table like you guys have done before to look at the relationship between 2 categorical variables, okay? Now, I selected this as a subset from another study, specifically because you have multiple categorical variable that you can select from, and you have one interval ratio variable, which you can calculate your mean, median, and standard deviation from, okay? So that is gonna be what you guys need to complete for next week. It is the lab. And then let me just find the specific spot where you guys can see. That is going to be in Course Connect, Lab 4 data. Okay. Here
I have a question.
Yeah.
Is our final project, you said that's due the 21st?
No, it is
Oh,
great
okay.
clarification. Everything will be due the 28th, but I will introduce it the 21st.
Okay.
Yeah. Yeah. I'm so sorry if I caused an internal panic. That was not the goal. Yeah, I'll introduce it. This way you guys have an opportunity to ask questions. I'll give you some ideas on what you can do. But yeah, that's when that's going to be due. Okay, so, okay, I need to share screen again because somehow it disappeared. Can you guys see Course Connect? Okay.
Yes.
So this, you're not going to use this data, so we're going to hide that. Today we're going to do chapter 10, but if you look right here, lab 4, this is the data set and the instructions are right here. Turn in your 4 separate analyses. You must include 1 mean, 1 median, 1 standard deviation, and 1 crosstab analysis. So you'll open up the Excel document, get that done, copy your results. For some of you, I'm still getting the problem where what you submit is the original data set and there's no analysis. So I would instead just do your analysis, but then copy and paste it into a new document that only has your responses, and then you can submit it over here. Okay, questions about lab 4? Pretty self-explanatory, pretty quick, clear? Okay, all right. So today we are doing chapter 10, which is the chi-square test. You guys still can't see that. What is happening? Okay, here it is. Can you see it? My second screen is acting weird, so it's not showing up. All right, let's click slideshow. Can you see it big? It says the chi-square test and measures of association. Okay, thank you, Diana. Okay, so let's talk about what we're going to cover today. We're going to summarize why we use a chi-square test in the first place. We're going to learn how to calculate and interpret this test for bivariate relationship. And this is specifically between nominal and ordinal data set. So it is not for interval ratio. We're going to determine the significance of a chi-test or chi-square test statistic. And then we'll explain the proportion of reduction of error. So well, I won't dive into it because we'll talk about it in just a minute. We will also just briefly talk about these. Whoops, it just disappeared again. Okay. It is like a technical difficulty night. Okay, we'll talk about these specific associations, but we're just going to touch on them a smidge because you don't need to know a whole lot about that. And then we'll talk about what the SPSS output looks like. Obviously, in this class, we don't get to practice with SPSS, but I still want you guys to see it because if you look at a peer-reviewed journal article, that's how they would talk about it. So I just at least want you guys to be exposed to it slightly. Okay, so that's the goal for this evening. Let's dive right in. So this is how you would show specific data. This is gonna look similar to a cross-tab analysis, right? Because in this first one, we're looking at the percentage of men and women who are first-generation college student. So you see the variable first generation, either they were first or non-first, and then you see the split between gender. So hopefully this kind of table looks very familiar to you because when we ran a cross-tab analysis, that's exactly what we end up doing, right? So you have your N. This is the sample size that falls in that category. Those are men who are first generation college students. And then men who are non-first generation are right here. And then you see the percentage split between the two. So based on just this column, what would be your interpretation of this data? Just men.
That more men were non-first than first.
Okay. Now, non-first generation probably means what?
They
That,
could have been. By all means, yeah, go for it.
That's okay, Sabian. Go ahead.
Okay. Well, it basically just means that they could have been like the second, third, or fourth generation of college students in the family.
Right. So there's likely somebody before them that went to college. Why do we care about that? Why is that important? First generation, non-first?
Because that usually kind of plays a factor into like the difficulties like a person might experience in college.
Okay.
And what resources they have connections to.
Right. So if you're the first one in your family who's like, I think I'm going to go to college, there is no one else then in your family who could go, okay, so first we're going to need to fill out the FAFSA so that we figure out financial aid. Next, you're going to need to work on finding recommendation letters. You'll need to talk to your school counselor and get that all set up. And then you'll need to make sure to take the SATs or ACT, whatever's being done at the time and region of the country. You get some mentoring and coaching as you go through to know how to do it. Similarly, once you are in college, once you've gone in, you have mentoring and coaching as to what that's like, how to manage your time, how to help out in terms of jobs so you're financially, adept and know what to do. So being a first generation college student comes with its own set of challenges above and beyond just being in college, right? So that's why this is a variable that you'll often see being measured. And then they compare it to gender, socioeconomic status, right? Racial group, all of that. There's a lot of deep data on that. You can see here the split for women as to whether they are first or non-first generation students as well. What do you notice about these numbers?
There isn't as large of a gap.
Right. It's much
For
closer.
women.
Absolutely. There's still a small difference, but it's much closer together. So looking at this table altogether, we see a pattern, or there's an association that exists between gender and being a first or non-first generation student. And it seems like men are more likely to be non-first generation college student than women. Okay. So now we take this data and we strip away the association. So this is hypothetical data. This table on the right, this is not real. I should probably go back and say this is probably not 100% real, but anyway, this is just hypothetical to show that there is zero association between gender and non-first generation student. And how do we know when you look at this table, how can you tell that there's no association?
Because all the
Because
numbers.
That's okay. I love
Oh,
participation.
because all the numbers are essentially the same, whether male or female.
Right, they're identical. So really, there is no difference as to whether you're a man or a woman for first generation, and there's no difference if you're a non-first, which negates any impact of gender as an association with whether you're a first generation college student. Okay. So this is kind of just a backdrop, right? So a chi-square test is an inferential statistical technique to test whether there is that association between specifically nominal or ordinal variables that are organized in a bivariate table. A bivariate table is just like a crosstab table. It's just what we looked at. It's the same thing we looked at when we talked about the size of fire, firefighters, and property damage. Okay. It's one of the most widely used tests that we have in the social sciences, and it has no prerequisite. Remember, we're talking about central limit theorem, normal distribution, right? This holds none of those. So there's no assumption about the shape of the population distribution from which the sample is taken from. And it's usually the way it's done is you look at the actually observed frequencies in a bivariate table, and then you compare those to what you expected to see. Okay. So if the observed and expected values are really close, then the chi-square statistic will be very, very small. But if the disparity is very large, then the statistic will also be very large. So the idea is if my expectation is that there's no difference, right, between groups, that's my expectation. If the actual behavior shows, whoa, there's a massive difference, then those scores are going to be really disparate from one another. My expectation and the actuality are going to be massively different. Okay. So if what you expect does not match the reality, we need to find a way to, address that. Okay. Hold on one second. Do you hear that? Yes. Thank you. I don't know if you guys can hear. My cat is like, meow, meow. Could you guys hear that? Oh, it was driving me bananas. Meantime, my son is right here and he's just playing on his computer. I'm like, go feed the cat. Okay. All right. So let's talk about goodness of fit. So a chi-square test, I should say, can also be applied to a distribution of scores. That is what's called the goodness of fit test. So it compares the actual distribution of the scores with a set of expected frequency. So it's the same idea. We figure out what it should look like, and then we compare it to what is the reality. So the question comes down to how well does the data fit what we would expect it to fit, okay? Again, we come up with these expectations because we have a wealth of literature we can go back to that allows us to create hypotheses and come up with an idea or a prediction in some way as to how data will behave, again, because of past instances. So that is how we get our expectation. But then we measure data, right? We look at what is actually happening, and then you make a comparison between the two. So if the data doesn't fit the expected frequency, then we have statistical significance, okay? So an example of that would be, and this feels almost like it could dip its toes into the political pool, and that's not my intent, so don't take it as that. But if you're looking and you're measuring temperature and you look at the last 50 years and you say, usually in the month of March, the average temperatures were 45 degrees. I'm going to make stuff up here, 45 degrees. And then this year, the average temperature was 56 degrees. Well, the expected value does not match the actual value, okay? That implies statistical significance. They are not behaving in the way that we thought. And so then you would insert the reason why you hypothesize that that's the case, right? Some might say global warming, others might say measurement error, others might, whatever it may be. Does that kind of help? Slight example of that? Okay. So again, the key idea is to compare observed and expected frequency in each category. Observed frequency is defined as the number of people who are actually found in the study to fall within that category or that specific cell. The expected frequency, on the other hand, is the number of people in the category that are expected if the null hypothesis were true. So in our men and women and first generation or not example, the null hypothesis may have been there is going to be no difference with men and women. It's going to be identical. So remember that second table to the right, it showed identical values for men and women. That could have been the expected value, right? If I had some good data to base it off of and historically, past literature supported that, that could very well be it. And so then I look at that expected value, which would be the null hypothesis, that there's no gender difference. And then I insert the actual data. What did I actually see when I measured within a certain university? And if there's a significant difference in those values, then it shows that there's something at play here, right? That is above and beyond. We'll talk about p-values with that. So that would be above and beyond error, right? I would be 95% confident that that was actually because there's a relationship or association. Okay. So this is what the distribution or the calculation looks like. So this is this is a terrible drawing of a chi-square. Let me show you. Oftentimes it'll be really italicized like that. I'm not sure whether that's better, gang. Let's just be real. It's not very good. And here's, okay, so it's an italicized X. That is the chi-squared, okay? And it is the sum of the difference of the observed value minus the expected value squared divided by the expected value, okay? So that is how I calculate my chi-square value. All right, so here's an example. There was a study done in 2009 as to the representation of male versus female characters for cereal boxes. Again, I don't know who comes up with these ideas. I don't know why your textbook is drawn to such odd ideas, but this was it. So the question was, what is the observed and expected frequencies for the gender of characters on cereal boxes? Okay, so if the total is 1,386, which let's pause and just think about that. That is a lot of cereal box characters. The expected would be 693. That would be divided half and half, okay? Half would be male, the other half would be female. That is the expected frequency if there is no gender impact on the character, okay. And just sneak peek, let's go back and look at it. What do we see here?
Mainly male characters.
Right. Which when I first looked at that 3 years ago when I taught that class, I'm like, how's a tiger male or female? But then you have to remember, what is the mascot's name? You guys remember? Who's this?
Isn't it Tony the Tiger?
Tony the Tiger. That is a dude's name, right? And who's that?
Sam the Toucan?
I think it is Sam the Toucan.
Oh, the name's literally right there on the box. It's Sam. Toucan Sam. There it is.
There it is. I didn't even see that. But yeah, you're right. It is Toucan Sam. So again, I suppose it could be Sam for Samantha, but I'm pretty sure it's Sam for just Sam. I don't know why I put those two back here, but again, Rice Krispie. What's that?
Oh, what's even better is that he also has his nephews in the commercials too. So like there's even more male representation towards Fruit Loops. So it's great.
Why wouldn't you pick a female thing? Anyway, and then obviously Rice Krispies, what are their names?
Snap, Crackle, and Pop.
Snap, Crackle, and Pop. You got it, right? So in our Snap, Crackle and pop, female or male?
Male.
They're male, right? Okay, so the ones I showed here, they happen to all be male. But again, if there was no gender difference, then it would be an even split, 693 to 693. Here's the observed frequency. This is what we actually found. 996 had a male representation versus 390 that had a female representation. Okay, so you would run the difference, right? I'm going to go back real quick. Don't get whiplash. I'm going back to this formula, right? So observed minus expected squared divided by expected. So that's what's happening here. So I would do observed minus expected. That gives me 303. I square it, which we do that to just take away the negative value, right? So it becomes an absolute value. And then that gives me this value, 130, once I divide it by the expected value, it's 132.48. Interestingly, the same values are true over here. So for females, 390 minus 693, that gives me negative 303. I square it, which is 91,809. And then I divide it by my expected value, which is that 693 value. And I end up with 132.48. Okay. All right. What do I do next? Well, I kind of just talked you through all of that. So it's doing the sum. This is the last bit, right? We did this entire section here. Now we need to sum it, and that gives me 264.96. Okay. So this is a quick reminder. How did we do this? First, you determine the actual, the observed, and the observed frequency for each category. Then you need to determine the expected frequency. The expected frequency is going to be a little easier to figure out because that's more theoretical. And it's usually going to be supporting the null, which is that there's no difference. So all of the expected values in each cell are going to be the same because it's essentially negating that there's going to be any difference. So it just divides them up equally. Okay. So in each category, you then take the observed minus the expected frequency. You square each of the differences, divide each of them by the expected frequency, just like we did here, and then you add up the results for all the categories. And you see you end up with your final value. Oh no. This is just a day of technical errors because now your faces have all disappeared in my computer. Can you guys still hear me?
Yeah.
Yes.
Yeah.
You can. Can you see me?
Yep.
This is so bizarre, you guys, because I can't see you at all. My screen just went black. Okay, well, we're gonna go with it. Do you see the screen? It says the Chi test goodness of fit.
Mm-hmm.
Yes.
Oh, okay. All right. So we need to figure out degrees of freedom. So we've done this before for other tests. Do you guys remember degrees of freedom?
Yes.
Okay, so how did we figure out degrees of freedom? You guys remember that before?
Like the total number of the sample minus 1.
That's right. So you figure out, okay, sorry, I'm gonna try this again. Oh, you guys all reappeared. Okay, let's see if now, no, you disappeared again. No, you're back, okay. Okay. This is just technical difficulty night. Okay. What is happening? Okay. This works. But this, okay. Can you guys see the screen? I'm not going to touch anything else. So again, the
Yes.
degrees of freedom
Yeah.
is your total number, in this case, of categories minus 1. In the past, when we've done degrees of freedom, it's been our entire sample size minus 1. This is number of categories, okay? So if you're doing gender, right? depends on how you're measuring it, 2, 3, 4 categories, it'd just be that -1. Race and ethnicity, same thing. You just take that number of categories -1. Okay. Okay. Now, chi-square distributions. So it cannot be less than 0, but it can be very large numbers. As we saw, our chi-square value right over here was 264. That's massive, right? We would never get that with a z-test or a z-test, obviously not with a correlation because it ranges from -1 to 1. So with a chi-square, it will never be negative. Now, why will it never be negative? Mathematically, it's impossible. You guys remember why?
Because it can't be less than 0.
What's that?
Because it can't be less than 0.
Right, but why is it, what are we, why is it impossible for it to be less than 0?
Is it because you can't interview like negative people?
I suppose that's true, but mathematically, what makes it so it cannot be less than 0? What is-
Square.
We square it, right? Okay. So if we go back to our formula, right, we look at the difference and then we square it. Okay. So right away, we're never going to have negative numbers. And then because we sum all of the different categories, then we're adding. So we're taking a positive value and adding other positive values to it. So it can never be negative. Okay. So you see here, these are different distributions for different degrees of freedom. So if the degrees of freedom is 1, that means there's only 2 categories, right? But you're doing 2 minus 1. You see kind of a sharp incline here, or decline, I should say, like a big slope of it. The more categories you get, the gentler the slope becomes, okay? So as the degrees of freedom approach infinity, the distribution becomes more and more normal. Because obviously neither of these look like normal distributions, right? Quick reminder, a normal distribution looks like this, right? Okay, this was my graph. So I would say these two right here don't look anything like it. And as you get bigger and bigger, they start to look a bit more like that, okay? All right. So for that goodness of it, again, you're looking at the levels of a single nominal variable. So how well does the observed frequency distribution fit the expected frequency distribution? And the question is always, is there a mismatch? Does it meet what I expected, or is there a huge discrepancy in my scores? All right, so we can look, again, your textbook has in the appendix a whole table of them. And the way it's labeled is you look down at the degrees of freedom, right? Whatever those might be. And then you're going to look across at the significance level. Now, which significance level do you think we're going to be using?
0.05.
0.05. Always a good bet, right? We're looking at 95% confidence at the 0.05 level, okay? These values here are the cutoff of significance, so that if your score is above that, it shows significance towards a p-value smaller than 0.05, okay? So again, you would look at the number of categories minus 1. You'd look down the column for 0.05 significant level, and then these are the critical values, meaning the point at which anything larger than that is statistically significant. Okay, this is another way to look at it. So this is for the a chi-square distribution with degrees of freedom of 1, showing the cutoff for rejecting the null hypothesis at the 0.05 level. So here is the value. I think we can go back and see, what was it? It was like 4 something, or here it is, 3.841. this is labeled right here, 3.841. Anything bigger than that is statistically significant. What was our value? 264.96. So is this statistically significant?
Yes.
Yes, very much so. In fact, any value above 3.8 would lead to a significant result, statistically significant result. Okay, this is way down the line of infinity, very much significant. Okay. Statistical independence is the absence of an association between two cross-tabulated variables. So when there's two variables that have zero association, for instance, I could say, all right, I'm going to predict that if you have brown hair, you are going to have a higher GPA at Aquinas. And if you have blonde hair, you're going to have a lower GPA. Totally made up. Doesn't make any sense. There should be no association, right? So if there's no association, one can say that they are statistically independent, right? There's no relationship there. The percentage distribution of the dependent variable within each category then should be identical, and there is no covariance because there's no overlap, there's no association. They're completely independent of one another. Okay. Now, when you do hypothesis testing for chi-square, first off, you're going to make an assumption or some sort of, you're going to go back and look at the literature and have some sort of hypothesis, okay? Second, you're going to state the research and the null hypothesis, and then you're going to select your alpha level. Your alpha level should always be 0.05. Just always keep that. And remember that your research hypothesis would be in the direction that you're thinking it should go, right? For instance, there is an impact or there is an association between gender and whether you're a first year or first generation college student. That would be a research hypothesis. The null hypothesis is the opposite, and it states there's no difference, which would be there is no difference between men and women and their rates of first generation college attendance. Next, you select a sampling distribution and you specify which test statistic you would run. In this case, we are running chi-square. You would then compute it, and then you make a decision as to whether you reject or fail to reject the null, and then you interpret your results. Okay, so these hypothesis testing steps are very similar to t-test, correlational analysis, z-test, all of that. It's repeating itself here because we go through the same process every time. Okay, there is no assumption with a chi-square distribution as to the shape of the population distribution. So this is huge, okay? But it does assume random sampling. I'm sorry. And it can be applied to variables at both the nominal and the ordinal level of measurement. Can it be applied to interval ratio?
No.
It cannot, okay? If you were doing interval ratio, we would be doing a totally different analysis, probably a correlational analysis, maybe a regression, but we would not be running a chi-square analysis. Okay, so first you state your research hypothesis, okay? And that is to say that the two variables have an association, right? That's the research hypothesis. There is an association. They are related in some way. And the way that we're expecting is that gender and first generation college status are statistically dependent, okay? So I'm swapping the words here. Statistically dependent means they are related. As one increases or decreases, the other one is impacted by it. The null hypothesis states that there is no association, okay? So it would state that gender and first generation college are statistically independent, okay? As one varies, there's no impact on the other, okay? So they are not related. They do not have an association. Okay, so then you figure out what is your expected frequency. So the cell frequencies that are expected in a bivariate table, if the two variables were completely statistically independent, that's how I do expected. If If I'm doing observed, then I actually observe the data and plug that in, okay? So really the chi-square test is based on a cell by cell comparison between the expected and the observed frequencies. That's what we're doing. So now let's plug that in. So if, where is this here? I want to make this smaller and move it up here. All right. So if I'm calculating it, first I need to figure out what is going to be my expected frequencies, right? Okay. So then I would go through and make my calculations. So to calculate the expected frequency, I take my column marginal multiplied by my row marginal divided by n, okay? Do we remember? So row and column marginals, those are the extra bits right here at the end. Here's what it would look like, okay? So there's of the, and I can go back here so that hopefully you guys will see how that would make sense. There's 817.414. Why is that? Okay, let's go back. Let's do our totals are down here. And this is the expected values for my first and non-first generation student split by men. And again, women would be first versus non-first. That is the expected frequency. That's if there's no association. So I would be taking this 41.9% times my marginal, okay? So if I'm figuring out what is that number, that percentage, right? I have to multiply it. So if 41.9% of men are first generation, then I need to calculate that time my marginal. And that's how I would get these values. Let's pull it up to make sure that that all checks out. So I want to make sure I'm giving you guys, oops, the correct information here. Oops. Okay. So this 41.9%, if I do that times 1950, that gives me 817, which is this value over here. Are you guys understanding how that was calculated? Okay. I could do the same thing here. So 0.419 times 2,670. That gives me 1118. I don't know why. My decimal points are slightly different, but about the same. Okay. Oops. What is going on? Okay. Going down here to non-first. Look at that. If I have, here it is, 0.419, 1936. That's 811. Oh my goodness, I keep putting our faces right in the middle of that tab. That's not what I want. 0.581. Is that right? Yeah. So non-first here, I would do 58.1% times 1950, which gives me this 1132 value. I go back and do the same thing here, 0.581 times 2,670 gives me this 1551 value. Okay. Does everybody see how I came up with those numbers? So just going back, I filled in my chart and these percentage would be that there is no association, okay? This data would be given to you. You would get the percentage. You might have to figure out the actual frequency, but you just multiply it by the marginal, okay? Okay. So in order to get, again, my frequency of expected value, it's my column marginal times my row marginal divided by my total n. Here's my total n. All right, so the test statistics that summarizes the differences between the observed and the expected frequency that's the chi-square. That's how you calculate it, okay? So for each cell, you would subtract the expected frequency from the observed frequency. You square that difference divided by the expected frequency, and you do that for each cell. It becomes a summation, okay? As it says right here, sum the results, okay? Here's our formula again. So this is the observed frequency minus the expected frequency divided by the expected frequency, okay? This difference here, you make sure you square it and then you sum all of the different cells. Okay. So we can then look at our chi-square for this particular example. These are expected frequency, which we saw earlier. We were able to calculate them. These are our observed frequencies. Again, those would be given to you. Then we go through and we actually do the calculations for it. Here's what it would look like. So you have, these are all the cells. It's just written a little bit more cleanly, I find. So it's your observed frequency minus your expected frequency. That gives you this result. You then square it and divide it by the expected frequency. Okay, so this value here is 19.47. You go through and do it all over again, right? So observed minus expected gives you this value. You square it and you divide it by the expected value, which gives you 14.05. The last step is doing the sum, okay? So then you would have to add up all four of these cells, which gives you a total of 58, okay? So that is your chi-square value for that difference, for the observed and expected values for gender and first-generation college student, okay? Are we tracking how I did this? I can't see all your faces, so hopefully this makes sense a little bit. Okay, please stop me if it doesn't. Okay, going back to the chi-square distribution, it is positively skewed because it never dips into the negative, right? It is always going to be a one-tailed test. And the number of degrees of freedom, as they increase, the distribution becomes closely and more closely aligned to a normal distribution. That's what it turns into. Okay. All right. So the degrees of freedom in a bivariate table can be interpreted as the number of cells in the table where the expected frequencies are free to vary given the marginal totals are already set. Okay. So this would be row -1 and column -1 multiplied together. So let's look at that. Okay. This is a contingency table that shows marginal and one cell observed frequency. Okay. So there's the total for each row and for each column, right? Total for each column is right through here. Total for each row is right through here. Only one cell is allowed to vary. Okay. So only 28 is free to be whatever number it wants. The other 3 cells are fixed. So that means we have 1 degree of freedom. The other 3 numbers will have a value that's determined by whatever 28 is. This is getting down in the weeds as to how we get degrees of freedom. Just let it in and then let it move past you. Don't worry so much about this. Okay. This, though, we need to be mindful of. Okay. This is the chi-square distribution. If we only have 1 degree of freedom, again, this is what the distribution looks like. It is a sharp decline, right? You get a very, very high score at 0. As we move to 1, it goes down, goes down, goes down. Notice none of these lines here ever touch the x-axis, okay? This really goes into infinity. You could have the highest value known to man, right? Again, the larger the difference between your observed and your expected value, the larger your chi-square value will go. But the greater the degrees of freedom, because we see here going from 1 to 5, already our distribution has changed, and from 5 to 9, it changes again. And this is approaching, starting to at least, it's approaching a normal distribution. Okay, a little tidbit about it. Okay. I don't want you to know anything about Yates' correction of continuity. So you're going to pretend you didn't even see the slide. We're just going to move right along. Okay. So how do we go about testing the limits of a chi-square test? So a chi-square test sadly does not give us a whole lot about the strength of the relationship. When we look at a correlational analysis, for instance, the closer we get to that 1 or -1 value, the stronger we know is the correlation. That says, whoa, this association is massive because it is approaching a slope of 1, right? As one variable increases 1, the other variable increases 1. That's almost like a perfect, relationship. The chi-square test does not give us that insight. We don't get to know how strongly related they are. It is very sensitive to sample size. The larger the sample size, the larger your value will be, which that's not surprising, right? The larger the sample size is in pretty much any study, the greater the potential for significance. And it is sensitive to small expected frequencies in one or more of the cells in the table. So no cell frequency should be less than 5, otherwise it's going to get screwy for the whole test. So let's give another example. Okay, so this is from the General Social Survey that was taken in 2014. It's the father's degree by the respondent's degree. Okay, so here's the idea. It's presupposing that you will get a similar level of education as your father. So if we know your father's level of education, we will have a better sense as to your level of education. So this is the respondent's degree, and this is the father's degree this way, okay? So looking through, what patterns emerge or what do you notice? Or maybe I should phrase the question differently. If your father has less than a high school degree, are you more or less likely to then go on to college?
Less likely.
Okay, and how did you figure that out, Diana?
Because when you look at like the father's degrees, as the father's degree increases, so does like the some college or more.
Very good. So what Diana is saying, and Mallory, it sounds like you have the same idea, is that as you're going to the father's degree, right? Okay. If as you go through, it seems to point to a respondent's degree of either high school, same, or greater. If we look here, if the father has some college, the respondent falls right in this category right here, 75%. So the more education the father has, the more likely the respondent is to have a higher level of education. Okay. In fact, if the father has less than high school, the highest cell here is a high school degree for the respondent. That's still higher even. Then it matches up here for high school and high school. Okay, is everybody seeing how we're looking at this chart? Does that make sense? Okay. All right. So making some assumptions. If we were to take a random sample of 897 individuals and we looked at the level of measurement as an ordinal level specifically for education. Another one you could do is health. You could do good health, semi-good health. Another ordinal level would be your year in college, whether you're first, second, third, or freshman, sophomore, junior, so on and so forth. Okay, let's look at the research and the null hypothesis. So your research hypothesis is that there is in fact a relationship between a father's educational attainment and a respondent's educational attainment. Okay, there's a relationship there. So they are statistically dependent. The null hypothesis is that there is no relationship and that they are completely statistically independent. Okay, notice this is the key difference here, dependent versus independent. For this one, they're breaking all the rules. They decided on an alpha of 0.01. Your textbook makes me angry at times. 0.05 is the way you guys should go. This one, they chose 0.01. So we're going to select a sampling distribution and a test statistic. In this case, we are going to be using a chi-square. Okay. So the way we would go about doing that is the levels of education minus 1. So it's levels of education for the respondent, levels of education for father of the respondent. So in both cases, it ends up being 3 minus 1. Because if we go back over here, there's 3 categories, right? Less than high school, some college. Okay, sorry for the whiplash. Here it is again. So it's 3 minus 1 times 3 minus 1. So it's 2 times 2, which is 4. Okay. So this here is our degrees of freedom that we're looking at. The chi-square obtained is then 180.58. And the way we calculated that is like this. So we take our observed frequencies for each of the cells minus our expected frequencies. Okay. Now we would get the expected frequencies by saying there is no difference. Okay. That there would be all the same. So if we go back, sorry, I just want to make sure that that's clear. Okay. These are the cell values that we observed. Okay. So these are the ones that are listed right in here. Shoop. Does that make sense? These numbers are all the same. These expected values, these are more theoretical. That's saying if it was all equal, this is what we would expect based on the, remember how we calculated that formula earlier for the frequencies? We would take each percentages by the total of our marginals, right? The column marginal or the row marginal. Then we would run the difference between the two values, square it, and divide it by the expected value. You would then sum this, add it all up, and you end up with 180.58. Okay, so that is our chi-square statistic. Okay, we would then go back to that chart we talked about that's at the end of your textbook and figure out what is our critical value. And in fact, the critical value is way, way less than that. It's like 6. So the probability of observing our obtained chi-square of 180.58 is not only less than 0.01, it's less than 0.001. Okay. This allows us to reject the null hypothesis. And finally, our conclusion is that there is in fact a relationship between the father's and the respondent's degree. As a father's education increases, so does the respondent's. That is the relationship between the two. Questions about that? Does that make sense? Okay. I want to make sure I'm not missing a hand here. Okay. All right. So looking at just overall measures of association, as a single summarizing number that reflects the strength of the relationship, we can look at that measure of association as the way to go. So we can measure, both associations for nominal and ordinal values. But unlike the chi-square, measures of association reflect the strength of the relationship and sometimes even reflects the direction of the relationship, whether it's positive or negative. Again, we see that with correlational analysis quite clearly. Measures of association also indicate the usefulness of predicting the dependent variable from the independent variable. Okay, that would be more in line with a regression, where you are able to predict where another score will be on the line of best fit. Okay. These are those 4 measures of association. I don't want us to get down in the weeds with those because again, those will all be seen on an SPSS printout. And if we were in a lab right now, I would show you the differences, but we are not. The bottom line is that you need to know for this class in this semester that Pearson's correlation coefficient that we talked about before is used for bivariate association, again, between interval ratio. We already know about Pearson's R. That's when we did a correlation. It ranges from -1 to 1. You know the strength of the relationship. The closer it gets to 1s, the stronger the relationship. Closer it is to 0, closer to no relationship. And you know the directionality of the relationship depending on that score. If you get a negative score, you have a negative slope, meaning as one variable goes down, the other variable goes up. A positive relationship is as one variable goes up, so does the other. Or as one variable goes down, so does the other. Okay. Pearson's R is the measure of association I want you guys to keep in mind. Okay. This we know already, right? This is the range of scores when you're looking at a Pearson R. When you're at 0, there's no relationship at all. You go from weak, moderate, strong, very strong, and again, this idea of perfect, which you never really see in the social sciences, but if you're in the positive values, meaning you have a positive number, those are positive relationships. Again, if you get into the negatives, it's a negative relationship. Okay. These measures of association as a whole are based on this idea of proportional reduction of error. Okay. We have done this before when we looked at standard error and trying to minimize that as much as possible so that we feel really confident about the values we're getting. For the sake of this class, you guys do not need to know how to calculate the proportional reduction of error. You just need to know that when you're looking at measures of association, we are also trying to minimize error as much as possible. We only want to see, the relationship between the variables, and we want to make sure we're taking away extra noise that it could be, well, is it because of this confounding variable that we're looking at a relationship? Okay. So there's a few slides here that we can also kind of move past because we're not going to be calculating this. So we're going to pass all that. Okay. I think we're going to get past that too because that is proportional reduction of error. I should have taken these out so that it wouldn't actually confuse you. Okay, lambda is one of those that we talked about that you would get in an SPSS printout. There is some value in knowing what it does. It is an asymmetrical measure of association. Again, you use it with nominal variables and it ranges from 0 to 1. It will never go into the negative values. Again, nothing with those associations will do, okay? And it provides with an indication of the strength of an association between an independent and a dependent variable. This is key because again, the chi-square value does not give us the strength of the relationship, but you can calculate a lambda to figure that out, okay? So it is asymmetrical. We need to be mindful of that. So it's a measure whose value vary depending on which variable is considered to be the independent variable and which is considered to be the dependent variable. So this is a slight twist to our example from earlier. This is looking at first generation versus non-first generation, but instead of gender, we're now looking at Latino versus non-Latino, okay? So this is what we are seeing. For first generation, there are 55 who are Latino, 54 non-Latino, and in terms of non-first generation student, 32 are Latino, 100 are non-Latino. What interpretation might you find from this value, from this table, I should say? What do we think? is there a relationship between being Latino and not, and first generation and not? Oh, looks at this. Okay, so Hannah was saying for first generation, there's not much of a difference. Very true. Do we see a difference between non-first generation?
The majority of Latinos are first generation students, whereas the non-Latinos, the majority are non-first generation students.
Absolutely. In fact, it's almost like a 3-to-1 ratio, right? Between 32 to 100 that are non-Latino versus Latino if they're going to be non-first generation. Okay. So you see here, there's the marginals included. We have our column totals, we have our row totals, and our total participant was 241. Oops. Okay. So first, you want to find this error term. That's the first goal, okay? You are not going to be asked to calculate what a lambda is in this class. I just want to introduce it because it's significant to know the strength of the association, okay? So first, we find the mode of the dependent variable and subtract its frequency from our total sample size, okay? So our sample size is this 241 value. We have it right here, okay? And in this case, the modal frequency is 132, okay, which is found right over here. So that gives us a value of 109, okay? So going back over here, we would then do some extra work. Again, I don't want you guys to get too freaked out about the math. That is not the goal. We would then figure out E2, which is again, taking the total sample size for Latinos, which is 87, minus our mode, which ends up being 55. I do the same thing for non-Latinos. It's this 154 minus 100, okay? I get these two values and I add them up. That becomes my E2 total. To calculate lambda, it's E1 minus E2 divided by E1 again, okay? So it's that 109 value from the first slide minus 86 divided by 109, which is 0.21. Going back over here, we'd say, if we rely on students' Latino identity to predict their first generation status, we would reduce the error by 21%. In other words, if we simply look at racial identity between Latino and non-Latino, and we're trying to figure out how likely are they to be first generation, we reduce the error by 21% by doing that. Okay. If we use Latino identity as the dependent variable and first generation status as the independent variable, we obtain something slightly different. Okay. All right. Kramer, we're skipping. We're not doing Kramer. Don't even look at it. We're skipping Gamma and Kendall. Okay, now this is where we need to go. What does it look like in SPSS? This is what it would spit out at you. It would spit out not literally, SPSS is real gentle and kind and sophisticated, but this is the table that you would get if you're running a chi-square analysis. You would see your variable, right, that you're trying to see if there's a relationship and association with. So you see male and female, and then you would get exactly this, your observed frequency, expected frequency, you would see the difference, you would see the squared value, and then what is the quotient of it, right? Because you're dividing it by the expected value, okay? This is the way, and again, I'm grateful you guys have these slides, because if you guys were running SPSS now or in the future, these are the direct steps. You would point click to all of these values in order to get your chi-square analysis. And this is what it would look like. You would get, again, the observed N, expected N. This residual is the difference between the two, okay? And then you would get your chi-square value, your degrees of freedom, and this asymmetrical statistical significance, which is less than 0.001, okay? The way you would write that up in an APA format would be to state that the impact or the association between gender And what were we actually looking at? It was gender. Was it first generation student? No. Oh no, the character box, right? So the relationship between gender representation on cereal boxes, that there is an association between those two. In fact, it is statistically more significant to have a male character present on a box than a female. They are not equal. The chances are not equal. You're more likely to see a male character than a female character. Okay. And then you would write the chi-square sign, which looks, where am I? Like that. You'd be over here. You would then say chi-square, right? I would include my degrees of freedom. And then my value would be 2.64.96. I'd have a comma. P is less than 0.001. That's how I would write that up. So if you guys read a research article that's been published that presents data on chi-square, that is how they would report it in text. Okay. And you would inherently know that what is in the parenthesis is the degrees of freedom. So, you know, you're just looking at a category of 2, in this case, gender, right? And the cereal box piece. You know that is a massive chi-square, right? So if you're looking back again at your distribution, where is my dot? Okay, like that. And it's probably at 1, so this is my chi-square distribution. My critical value is probably right around here at like a 4. And then I'm way down here at a 264. So highly significant. Okay. Does this make sense, guys? Are we tracking how that makes sense? Okay. The biggest things you need to walk away from this course, specific for this specific lecture on chi-square, is what type of variable would you do a chi-square test with? What is the answer to that?
Ordinal.
Ordinal or nominal, right? Both of those work. Okay. Not interval ratio. Okay. And it is a test of the association, right? It is all it's presumptive on the fact that you are running a hypothesis, that you'll have a research hypothesis and a null hypothesis. Your null hypothesis states there's no difference, which allows you to fill in the cells with what would be a no difference between the independent variable and the dependent variable. Okay. Then you plug in your actual data. What did you observe? Okay. And then you look at the difference between what is observed and expected. And the larger that value, the greater the difference is, meaning what you expected did not happen. The smaller the chi-square value, the more closely the values are between what is expected and what you actually got, which would support the null hypothesis that there is no difference. Those are the big picture items that I want you guys to really have mastered. Does that make sense? Okay. Much like any other analysis here, I want to make sure I can show you. No. Okay. Okay, I need to find you guys all again. Here we are. Okay. This is a different different data set here. But if I wanted to run a chi-square, I would write equal, whoops, and I would start writing chi-square distribution, okay? So this returns the left-tailed probability of the chi-square distribution. You see here, this is the right-tailed probability. It's probably what I want here. This is a test for independence, so we can even do that as well with the appropriate degrees of freedom. So again, Excel can run it all. So I would select this one, you double click it, and then you need your actual range, okay? So this would be if everything were equal, the actual range is what you got. Those are your observed value. And then the expected range is if everything had been equal and there was no difference, what would that look like? Okay. That's how you would run it. And then it runs a comparison between those two, the same way we did by hand. So you could do it the hard way with the calculations. You could do it the Excel way, which is click, click. Again, in SPSS, it's just as simple as just a point and click. You are not being asked to run a chi-square test for this lab, for lab 4. You could do that for your final project if you want to dabble in it, but there's no expectation that you would do that. Okay. Questions for me from this evening's lecture? How can I help? You're like, we good, we got this. Stats is our life. You guys, if any of you guys told me you went to graduate school to like study more stats, you'd make my day, probably my year. Don't expect that to happen. It's okay. My expectations are very low. Anybody that goes into graduate school will have to do more statistics. So in the end, I win, right?
If I tell you that, can I get extra credit?
If what?
If I tell you that I'm gonna major in that, can I get extra credit?
You will have my infinite admiration. No one needs extra credit in this class. Everybody's doing great. So that's not a necessity. But yeah. Okay, so for next week, make sure you complete your lab. You have a lot of flexibility as to what you want to do. Please remember, there is only one data, one variable that is an interval ratio. So hint, hint, the mean, median, and standard deviation needs to be done on that one variable, okay? So that should be fairly straightforward. And then you can select a crosstab between any two other categorical variable that you find would be interesting to look at. Okay? All right, that's all I've got for you. We will then see each other next week. It'll be the last full week of lecture. The week of the 21st, like I said, I will introduce the special project and I'll go over a review so that everybody's feeling prepared and ready to nail the final. Sound good? The final is not the 21st. The final is the 28th. Yes. What's your question?
May I ask you a question? On the syllabus, I noticed that there's a quiz 4, so I was just wondering if we are having that or are not having it, just so like we can prepare if need be.
So you broke up just a tiny bit there. It says that there's a quiz 5.
Oh, 4.
Quiz 4. Was the last quiz 3?
Yeah.
Yeah. I think it's because I switched the schedule around. There are no more quizzes. This is the last lab. There's no more quizzes.
Okay.
That is not going to negatively impact your grade in any way. Usually what I do is I'll run 4 quizzes and then I'll drop your lowest score. Everybody's done really well on the quizzes. If I've sent you a note though that said, I can't grade your paper because you sent me the whole document again, please double check those notes and make sure you send me something I can utilize to grade. That would be my only advice on that one.
Okay. Thank you.
Okay. Thank you for the message, Hannah. Okay. All right. Well, you guys have a wonderful evening and enjoy that warm weather. And we'll see you next week.
Thank you.
All right.
Thank
Bye-bye.
you.
Thanks, Professor. Have a great week.
Thank you. You too.